Okay, as Rick mentioned, I'm Jeff, and this is work with, I'm at UC Santa Cruz, and also Carlos Maltzahn, who's also a professor at UC Santa Cruz. And today we're going to talk about, goes down a little bit, kind of a follow-up, because then, this is a little loud, maybe. And last year, we gave a presentation on our initial implementation of Skyhook, which uses Ceph object storage with programmable extensions. And since then, we've added quite a few interesting features that I think people might be interested to see. Let me see if I can kill the... there you go. Sorry about that. Okay. Okay, thank you. So first, let me say this project is supported by CROSS, which is the Center for Research in Open Source Software at UC Santa Cruz. So it's a newer center, a few years old. It's pretty dynamic. And the goal of this is to sort of help students understand open source and develop these projects, right? So we want to bridge the gap between what students do for research and what companies and entities do in the real world. It was originally funded by Sage Weil from Ceph. And also, we have corporate memberships. So there's three primary goals. Teach students how to productively engage in open source, fund high-impact research that has potential, and then incubate developer communities around those same research projects that might have this potential. We have Carlos is our director, Stephanie Ligi, assistant director, and a few companies, Kioxia, Seagate, Fujitsu, and Samsung, we're very grateful to have, and an excellent advisory committee as well that give feedback about quarterly. And then also we have once a year presentations and workshops that people are welcome to come to. So there's a few incubator projects, which is what this project is part of. So I'm Jeff up there with the Programmable Storage project. And then we have two other ones. Kate, who works on getting poets to program AI, really interesting work, actually. And then Evo works on a reproducibility framework for scientific experiments. So there's some other details here that you might want to check out and take a look at the system. As I mentioned, there's graduate students, several graduate students working on different projects. And then, as I also mentioned, sets of research that's supported. These are pre-incubator projects. And then on the right is like the symposium that we have once a year that brings in industry to talk, as well as students and projects ongoing updates. So some pretty interesting speakers as well and keynotes. So consider that in the future if you're interested in this area. Okay, so that's my plug. And so today, as I mentioned, last year we presented the current status. And in general, this is scaling out storage to support database processing, right? So as I mentioned, it's storage extensions to Ceph. And what we're enabling here is in-storage execution via some data access libraries, which we've added some since then, and then also using their APIs. So these are going to execute in the storage layer. So that's sort of the overview of what Skyhook is. And in this talk, I'll give just a brief overview of what it does in general as a reminder and some new developments. So there's three primary new developments that we've had over the last year. One, previously we addressed row format, right? So we put data partitions and objects in a row file format and process them. And now we've added column-oriented storage. So we have now support for Apache arrow format in storage, which gives much better performance for column-oriented workloads like analysis, things like that. So that's interesting development. We've had more extension now for backend plugin support. So given these new formats that we supported Arrow, we actually had to build some kind of interesting framework to understand how to add new formats, not just Arrow, but maybe something else. So we consider scientific formats through HDF5 here, and a high-energy physics format called Root, which is a tree-based format. And then lastly, we've added physical design reorganization. So what does that mean? It means that we can dynamically change layout now. So in the physical design world and databases, typically you choose a design, a partitioning strategy, indexes, views, and this kind of thing. You do this up front, and you do this once. You may have dynamic policies for that, but that's kind of a database notion. And what we're doing here is we're extending that into storage, right? So we're going to let the storage be able to change the physical design, from format A and layout A to format B or layout B, add indexes and views, and consider that what is happening dynamically in the workload should maybe be matched by the storage. And we'd like it to automatically do that. We're not there yet, but we have an orchestration layer that we sort of trigger how to begin changes in physical design. But primarily you can think of it as row, turn to columns, things like that. What is data management and storage? So this has been talked about for a very long time. There's been software, there's been hardware. There's a lot of, even database companies have full vertical stacks, specialized boxes, things like that. Today, a lot of research is in hardware area with FPGAs and customized functions on hardware embedded. And then in the space that we're working now is distributed file systems. So we look at the Ceph object storage, and I think this makes exploring these ideas a little bit easier maybe, certainly more flexible to change things without having to worry about hardware and flashing things. So I think this is a nice space to be able to explore such approaches. So our approach uses object classing extensions in Ceph. So this is a library that's available in user-defined functions that are available in Ceph. You can define your own. It's open source. There's already some examples in there. You can write your functions in C++ or Lua, and you can think of them as sort of customized read-or-write methods. So maybe write includes compression or maybe slicing, right? These are methods that execute on objects themselves. So when the request gets to the object, if it's a write, I'll write plus maybe do something like add an index for where the interesting points are in this image, or whatever users want to write in their code, you could add that to, it's like an overloaded write function is a way I think of it. Similarly for read, right? You can read the data plus process it on the way out. So this is the kind of thing that we're doing. However, to be able to do that, we want to really provide the data semantics to the storage system, right? Because we would like the storage to understand what it's processing, when it's going to select or project or filter. It kind of needs to be able to understand itself locally at that object level. What does this data mean, and how do I interpret it to be able to process it correctly? And this locally notion means that these are methods that are executed on objects themselves. Okay, pushdown processing is kind of what we're looking at. So this is also not new, just as a quick overview of, typically you'd have a plan over there on the left, and it executes at the database application layer, so all that executes at the layer up top, and then down below the sources there are pulled out of the storage, and then they flow up, the tuples flow up the plan. So typically we just read in the data storage layer, but consider if you want to do a pushdown, maybe you like to push that select a little farther down. It's the standard approach. Right? So filter the tuples out before you do something else and maybe do a join. But then what if we would do this today inside the database application? So it's really just a logical flow that's executed in one place, right? The physical flow is actually executed in one place at the database layer. And what we'd like to be able to do here is read plus process the source data in the storage layer. So you think of those sources, you can think of access path selection and database optimization techniques. So we'd like to kind of separate these red and the blue, and we're going to actually push them down lower than normal. So in a plan, it's pushed down in this logical plan, but the physical plan all executes in one place. In our case, we'd like to split it and execute half maybe in the storage and maybe the other half perhaps in the database layer, where half is whatever the optimizer might say, right? So when we consider these plans and then access path selection down at the bottom, there's a lot in databases to worry about: replication and consistency, access control. And conveniently for us, a lot of it is handled by the storage system, right? So this is kind of a nice place to be, to not have to worry too much about that as you would if you would implement this from scratch or in your own database system. And then for physical design, we want to consider things like indexes, materialized view. You can think about partitioning and file format. So partitioning would be, how do we map data to objects? File format is maybe what format do we format each of those partitions into? And then we might consider data skew, right? Because object sizes, we want to maybe keep them uniformly sized. Maybe there's an optimal size range to keep the objects within. You'd like to be able to kind of continually keep the physical design in a optimization framework so that as the workload changes, you can make these decisions dynamically and maybe change the format or add an index, right? And then interestingly, so this sort of disks there along the bottom show, like maybe you have JSON format, maybe you want to support protocol buffers format. So we've shown how to support row format and this new arrow format, and now the scientific format. So I think there's a lot of flexibility in different formats you could support as long as you can embed those semantics into the object layer. And then the physical design right there at the bottom might change the layout on disk. That's basically what that means. So an overview of the architecture is, consider you have an access library up top, so a database application. or maybe a scientific library like HDF5, some file format interface. And then we would like to take the native ops from the database or maybe the file format interface and push them beyond the application. And the storage layer via, in databases, called external table interface, or Postgres calls it foreign data wrappers. HDF5 has its own sort of external mapping called virtual object layer that's new, that's very interesting as well, I'll talk about briefly. And then these native operations are pushed into the storage system onto objects, and that way we can operate on those objects in parallel. Where objects here will contain data partitions, which I'll show you in a second. So those are custom data partitions, however you'd like to do it, row, column, whatever branch, whatever you'd like. And then these little blue machines, they represent Ceph servers, where each server has a collection of objects that's mapped to it via Ceph's storage mapping algorithm. We don't touch that. And inside each server, there's a little RocksDB embedded. So this is like the local indexing mechanism for objects and managing them. But it's also open, so we can actually inject our own key value metadata into that RocksDB. And that way we can kind of locally queryable metadata about the objects that are in that server, right? And that makes kind of an interesting way to look up metadata and consider these views and schema changes and things. And the objects are the ones, as I mentioned before, that actually will apply the code extensions. So this is the current status compared to before. We have the same type of extensions, but we've added quite a few more for different types of processing. And now we have this dynamic reorganization, which an interesting aspect of that is because objects have their semantics, right? We want to consider each object independently, that it could be transformed from row to column or not. So you might have some that are row and some that are column, and these are kind of interesting avenues to explore research-wise and also performance-wise, basically to adapt to that changing workload. And another key interesting part here is we'd like to be able to support elasticity, right? So we are able to split objects now. And think of it as repartition. So maybe your object gets too large. You have data skew, as we saw before, maybe too many rows are inserted into one particular partition, and we want to be able to split that up so that it can be more of a balanced object size across the system. So to contrast with the column-oriented, so previously we had row-oriented, so we take table data, partition them by rows. In this case, we use a hash-based partitioning. And then it generates some data set that will format in a row format, which we use Flatbuffers for that, which is a fast in-memory serialization library. It also has an API for accesses. And then we take that formatted data and call that an object, and we'll write that right into Ceph. So this is raw blob you can write into Ceph. And inside that object, it retains the data semantics. That's the important part that we need to know for all these new techniques that we're going to be able to do. And those are what is interpreted by our custom classes. Importantly, we use generated object names because we'd like to be able to scale and not have to worry about having giant lookup tables to store like object names and partition mapping. So we just think of a generated function that generates the mappings. Keep this pretty simple. It's also very interesting in that it's constant time metadata lookup. And space as well. And that way we don't have to store any location in Skyhook. So if we think about a database, it doesn't really need to know where all the files are, what format all of them are, or in this case, where all the objects are and what format each of them is. We don't have to do any of that, right? We just have to keep track of how many objects are, how many partitions there are for this table. And inside the partition is what's encoded and embedded in itself as its own semantics. So it knows whether it's row or column, et cetera. So that separation kind of gives us a very nice scalability. We don't have to keep track of these things if servers go down or are added. Okay, so the first new thing is this column processing. So now we consider reformatting the table into Apache Arrow, which is also a fast in-memory serialization library. It supports column access. A lot of the backend for that would be Parquet as well. We could read and write in Parquet. We haven't actually added that. We actually read and write in Arrow raw. But you could do that if you want to save space for compression and consider the trade-off for decompressed time. And this was actually added this past summer as a Google Summer of Code project. So we had a student working for Cross in Google Summer of Code who added this Apache Arrow processing for us. What kind of processing types do we support? Consider these 3 objects here, partitions, right? So maybe 1 partition per object. You could subpartition those, but there's more details later if you'd like to talk about that. But still within an object, we'll map 1 partition to 1 object. let's say that, and we can do row operations, column-based operations, select and project. You can also do set operations, so you can think of like aggregate, like minimum, max, compute min or max, compute some sort, order, this kind of thing. We haven't added group by yet, but that's certainly possible given sorts. So there's some pretty interesting approaches you can do. So these are all functions that are added as our extensions to the read plus process. So you can read plus do some extra work. How do we embed those semantics? Well, given that we've formatted each object data blob into this Flatbuffers or say arrow, they already have their own metadata that you define, but you can also add more. So we've added a little bit more. You can think of it as key value pairs that you can add. Flatbuffer has a schema you can define. It also has something called a flex buffer, which is much more flexible, so you can think of a flexible schema. And then arrow has something where you can add your own schema metadata. So you can add additional key value pairs to their typical fields. So it maintains field information per column, and you can add your own. So we add a little bit of extra, like, what is the data format, and what is the data type or the column type. And it actually becomes kind of interesting because some types are available in Postgres, some types are available in Arrow, some types are available in Flatbuffers, and these are not. The intersection of these is interesting to see, right? So we have an encoding of our own that says, well, this is the Skyhook type that we'd like it to be. Whatever format then, that format can map it to the type that it supports. So that's kind of the extra metadata that we put in there. And then another interesting thing that came up when we add a new format is now if you issue a query, when the read gets there, you need to know what processing method to call with what library. Right? So this wasn't immediately obvious. One way you could do it is keep track of every object's format, but as I said, we don't want to do that, right? So we've embedded this inside the data blob. So inside every data blob of Arrow or Flatbuffer, whatever, we now wrap it with little metadata, which is a Flatbuffer itself. And all that is these, 6, 7, 8 lines, whatever they are. It's about 40 bytes. Right? And the important thing here is each partition then can open that object and read it. It can look at this wrapper and say, oh, what is this blob data inside? There's the raw data. That would be a serialized Arrow table or a serialized Flatbuffer. But right up top is the format. So it can check that and say, oh, it's format type Arrow or format type this or that, right? So it knows then what API to pass that blob data to. So that allows the object to know itself without having to consult the higher level or ask any other objects. It can go ahead and interpret its own metadata on its own. And again, it doesn't have to be all the same, right? Because I've mentioned some objects might be transformed to row, and some might be still columns or vice versa. So that's why this was kind of important. So given that we can do that now, we wanted to consider scalable APIs. So what does that mean for file systems, right? This multiple formats that have been enabled now typically are supported in database systems via external table interface. So you can consider an external table that's a file, a text file or a JSON file, or maybe an HDFS cluster, things like that. But we like to be able to just support a single file format through this similar type of interface, right? So we consider this HDF5 and this root file format. So I'll try to focus on just one of these for now, but HDF5 has an interesting aspect, that virtual object layer I mentioned, that allows an HDF5 file API to map onto itself. So if you think of that, it's an interesting mechanism to be able to scale that out, because you can take parts of that file now and call them new files, right? So take a file and you can kind of sub-file it out on your own and match it to your whatever layout you like. So that kind of matches our physical design implementation style. And that's a new feature. I don't know if it's quite out yet, but it's almost ready. It's pretty interesting. But basically, any file format that allows you to map it to other things would be able to fit into this framework. So consider this root file format. This is just a picture from their site about how does this do layout. So these are branches and trees, but essentially they look like columns. This is a high-energy physics file format. And what we can do then is we're going to take that, and instead of maintaining files and headers and where does this byte offset and this row start and that row, all this physical information, right? We're going to chop it into we take their trees, we can consider those as tables, right? And we can take these branches, we can consider those as columns. And then we can just call those partitions. So now if you wanted to get, say, the data out of some tree with some branch and some particular entry in that branch, you no longer have to look up, well, in the file header, where exactly is that piece stored. There's no physical mapping. You just declare, I'd like, tree X, branch Y, elements A, B, and C, or something like that, or elements whose properties are less than some value. So given that you can map a file format like this, if you can map a file format like this into some kind of partition mapping, it allows us to be able to do all of these interesting select and project and filters, the things that we've done with the database partitions. And then on the far right there, you can see that we're really just keeping track no longer of files and data sets and branches. We're just keeping track of a name, which I mentioned is regularized naming. So we can keep it like a data set name, dot a tree name, dot a branch name, dash A, say it's branch A. The other one may be branch B, and the other may be branch C. And maybe branch C, because none of these don't all have the same amount of data in each. If it's non-normalized, right? But the branch C there might be split over multiple objects. So that's also possible in our framework because we just need to keep track of how many objects are there. We don't have to keep track of their name. We don't have to keep track of anything. So when you want to query, if you know you want something from branch C, we can do that without having to consult any metadata. We can just generate all the object names for C and broadcast out the declarative request and say, please give me such and such, maybe apply a filter or select a project. So this is a way that you can think of to scale out the object interface. And since these, the file interface, excuse me. And since these objects are in Ceph, right, it's a big parallel storage system or distributed storage system. You can do all these operations in parallel. So presumably the names will hash to different locations, and this can all happen at runtime in parallel. Okay, in this particular format, that tree-shaped structure matched a column format. So as I said, if you can kind of map files to one of these type of formats in partitioning, you can kind of do the same procedure with them, right? So it's replaced by the collection of objects, and then not only is it scalable file access now, but the processing is actually scalable. So on your laptop, you can consider that now you can push down to select instead of getting back the data, looking at your file header, finding a particular data you want, and doing the filter there. You can just ask for it to push it down, and it could go out to any size system underneath. And there's no third layer on top, so you might think of adding like maybe a Spark or Apache Kudu or some processing layer on top of your storage. This actually happens directly in the storage. So a similar idea in scale out, but there's no extra system. It can happen right at the read byte layer. Okay, and then we develop a Python interface because a lot of scientists would rather use that than say a SQL or something like this. And the library looks like this. And the important part of this is just there's a client library. Then we have a Dask scheduler. So this is the thing that's going to issue all those reads. And those reads go into the Ceph cluster. So the only important thing for this picture is to show that maybe the user has a laptop. And each of these layers is independently scalable. Right? So the number of schedulers, if you have too many clients, you could add them. The number of workers, you could add. Those look like this, but they're meant to be machines. And then, of course, the Ceph cluster itself is scalable. So the storage layer is scalable, the worker layer is scalable, and the task schedule layer is scalable. Or you could push them all onto the same Ceph machines if you like. So it's a pretty flexible infrastructure, we think. Okay, and then lastly, the third new thing is this physical design management that I mentioned. So this is we published as a PDSW last year, and we do this physical transform between row and column. In this space, though, however, there's a very large choice of design possibilities, as well as intermittent design possibilities. So you could think of along the way, how fast do we want to roll out this design? This is a kind of interesting problem to consider. Oops. So as I mentioned, it looks like something like this. We have an orchestration layer that might coordinate between the storage clients and the servers, which objects to transform. Sorry about that. So there's two types of transformations. An object might transform itself locally. So on the left there, we have a row-based object transforming itself to maybe a column orientation. And then a distributed transformation, what we'll call as maybe multiple different objects with their rows, send their particular columns to other single objects that will contain an entire column. So this is a way to do that. As I mentioned, it's repartitioning. Maybe the sizes get too big or the workload doesn't quite match anymore. And so you're able to kind of dynamically decide to keep it local or split them, and it's sort of like a scatter-gather of different rows and columns. And of course, distributed is more expensive. So in contrast, what's the alternative? Well, today, you'd read it all into the database would convert it to maybe columns, and then you'd write it all back down. So interestingly here, this all stays in the storage layer, and in that case, it doesn't even leave the server, it just transforms itself. It's like read, modify, write. So some quick results to just show like how does this help us? If we consider TPCH workload, or at least a table from TPCH with 750 million rows, apply a filter, think of a 1% filter or 10% filter on Cluster and Cloud Lab, which is an NSF bare metal infrastructure, and then Postgres 10 and our Ceph extensions. So what we've done is we've generated an 8-node, this is just a single graph for an 8-node Ceph cluster, and there's 10,000 objects, and all of them are roughly the same size. We try to partition them so they're relatively even. If you do this local transform, this is the execution time, not for a query, but this is the time to transform it from row to column. And then the time to transform a distributed transform for one single column, you can see that's a little bit higher, and that's just for one column. So that's all objects giving a piece of their data set, which is say column A. All objects are sending their bits of column A to a target column A collection object. Right, so you'd have to do this over time for column B, column C, et cetera. And that's why I said the distributed transform is expensive, and you might want to consider a policy how to roll that out. And then the third bar there represents what if we did it outside storage. In that case, just to show you, we pull it all out up into the top layer, transform it there, and write it back down. So that has a lot of network read and writes, extra reads and writes, and network time there. So that's why it's important to consider the cost for transforming. And now if we look at one of those queries, if we look at execution time on the left there again, and then these three columns represent, the black column represents the time to do that select on that table. Extended price from line item where percent matches about 1% of the rows. That's the flat buffer format. So it's pretty expensive to do that in the flat buffer format. The second one is after we've paid the price to transform. On the previous slide, we have column format now, an arrow, and performance is much better there. And then the third one represents the most interesting case, which is when we're doing physical design, you may want to not only change the format, but you may want to collect column A, B, C, and D, et cetera, into their own little arrow tables. So now the partition is a collection of arrow tables, one per column. Or maybe if two columns are accessed, commonly you'd put those together. And that basically the savings there is we didn't have to read the entire blob, we just read column A out of that blob. Because when we transformed it, we put metadata in that RocksDB and said, here's where column A physically sits, and that's self-contained. So that's some of the benefits. And scalability, this just shows the execution time is if we push it out to some number of servers, it does in fact become faster to process, which is not surprising, but it's a good result. And then lastly, something very interesting that comes up is what is the CPU cost? So we can think of you do pushdowns, you're definitely going to save network costs, right? Because you're going to send back less data. In the previous case, just 1% comes back. Right? But if you don't care about network and you have infinite bandwidth, it turns out that the CPU cost to build all those packets is not trivial. So you're wasting all the CPU on your storage layer to build the packets, not just read the data, build the packet and send them. And on the top here is that case. So on the right-hand side, the storage machines, there's 8, like I mentioned, and that's sort of the accumulative CPU cost to send all the data back. Standard read, no processing. And this on the left side is the client. That's the client consuming all the packets. Right? So that's not trivial that you have to get all that data back. And then you're going to throw most of it away because only 1% matches. So then in the middle row, looks very similar because this is storage machines without any push-down processing. Right? So the storage machines are going to read the data there. It's not a standard read, it's one of our CLS reads. But in fact, no data matches, and there's no filter to be applied, but it's still formatting in the format, returning it to the client. And now the client is applying the filter. So you can see in the middle, the blue bar is a little higher than the top blue bar because it's applying that filter. In the top case, it was just reading the data like normal. In the middle case, it's actually applying the select on the client side. And in the bottom case, we're applying the select with our extensions in the storage side. So you can see the storage cost goes up a little bit there. It's not very much, actually, but it is a little bit, you can see. And on the client side now, it's down to almost nothing because it has no work to do. Right? It's not receiving many packets, only 1%, and it's not applying any filter because that's already been done. So this just shows you that network cost is not just the only thing to consider, it's CPU cost. And with that, I guess I'll leave it with that. Yeah, we'll take questions.
Maybe one question, because we started a little late. Any questions? All right.
Okay.
Thank you very much.
Thank you.